Hello everyone, welcome back to Basic Electronics classes. I am Lavanya Vaishnavi. Today I am going to take up the module 4, which is BJT applications, feedback amplifiers and oscillators. I am going to discuss regarding 555 timer in this session. So in this session I am going to cover the topic what is 555 timers, few of its applications and operating modes of 555 timer, and one of its application which is a stable multivibrator. Now, coming to the very first slide, let us understand what is 555 timer. So, this 555 timer is a versatile analog digital IC. So, what is this IC? It generates the pulses. It generates the pulses based on the inputs what we give. Based on the inputs what we give, it generates the pulses. Okay. So, now let us understand how does it look like. So first it is a 8 pin package. It has 8 pins. The first one is pin number 1, which is connected to ground, pin number 8 which is connected to VCC, and pin number 2 and pin number 6. These two are given to trigger inputs and threshold inputs. It is given to trigger input, pin number 2, and pin number 6 is given to threshold input. And you have pin number 3, which is where we take the output. So here we will be getting the pulses. So based on the trigger input and the threshold input, we will be getting the output here. Pin number 4 is to reset. If you want to reset the complete system, you will click on pin number 4. And 5 is the control pin. 7 is discharge pin. So this is where the capacitor discharge. Using pin number 7, the capacitor will discharge. So look at this. This is the physical structure of 555 timer IC. So this is a 555 timer IC. It has 8 pins. This is pin number 1, 2, 3, 4, and it goes on 5, 6, 7, 8. Okay, totally it has 8 pins. Coming to the applications, what are the applications of 555 timer? So this is mainly used to generate the pulses. So it is also used for generation of square wave. Where do you use this square wave or where do you use this pulse? First I'll tell you about pulse. See, you might have remembered the SR flip-flop, JK flip-flop. There you need clock cycle or clock input. For these clock inputs, we need the pulse generators. So, to generate pulse, we will make use of 555 timer. So, I can say that wherever you want or wherever you are using flip-flops, okay, wherever you are using flip-flops, there and all you can use the 555 timer. Next, it is also used in analog integrated circuits. It is used in TV broadcast. It is used in Morse code generation. This is one of the main application, which is Morse code generation. Okay, so in Morse code generation, we will make use of 555 timer. Coming to the next slide, which is IC 555 timer internal block diagram. So what is there in internal block diagram? In internal block diagram, you can find two comparators. This is comparator 1 and this is comparator 2. One SR flip-flop whose output Q bar is connected to the output. Okay. So the output of SR flip-flop, which is Q bar, that is connected to the output. You have a transistor which is used to charge and discharge the output. Now this is the 0.7 which is used to charge and discharge. Okay. The next is pin number 8, which is connected to VCC. Pin number 5, so which is a control. Pin number 4, which is reset. And pin number 7, which is discharge. I told you about the threshold, right? Here we will have a complete explanation what is threshold and what is triggering inputs. And this is the first input, which is ground. Okay. So we have comparator 1 and 2. So if you just look at the circuit, you have VCC, which is connected to 3 resistors. So each resistor is having a resistance of R, and this is also R, and this is also R. So all the 3 resistors will have the resistance R. So now I'll write the circuit. You are having 1, 2 and 3 resistors which is connected to ground. Here it is connected to VCC. Let me note or let me mark this point as X, mark this point as Y. Now I have point X and Y. I know that all the resistance values are R, R and R. It means that the voltage VCC is divided equally across each resistor. Each resistor, that is VCC is the total voltage applied. Therefore, each resistor will be having divided, or each resistor will consume 1/3 of VCC, correct? So, it consumes 1/3 of VCC. This also consumes 1/3 of VCC. This also consumes 1/3 of VCC. Now, what is the potential drop from X to ground? It is equal to 1/3 of VCC, right? 1/3 times of VCC. What is the potential drop from Y to ground? So, from Y to ground, it is 1/3 of VCC plus 1/3 of VCC, which is 2/3 VCC, which is 2/3 VCC. Understood? So, from point X to ground, it is 1/3 of VCC. From point Y to ground, it is 2/3 of VCC. Now, look at the circuit. Here, you can directly see that from this point, this is the point X and this is the point Y, right? This is the point X and this is point Y. So, at point X, the voltage drop is 1/3 times of VCC. At point Y, the voltage drop is 2/3 times of VCC. Okay. So, the comparator 1 compares the voltage 2/3 times of VCC with the threshold voltage, and comparator 2 compares the voltage, that is triggering voltage, with 1/3 of VCC and gives the output. So, these outputs are given to SR flip-flop. In SR flip-flop, the output Q bar is connected to the output. If you look at this properly, so you have a bubble here indicating that, so the output is inverted here. The output is actually inverted here. Now, look at this. So, comparator 1 compares the threshold voltage with reference voltage, that is 2/3 times of VCC. Comparator 2 will compares with 1/3 times of VCC. When reset is 1 and S is 0, the output is 1. When reset is 0 and S is 1, the output is 0. Okay. So, whereas the actual output is inversion of this Q. Okay. Next. So, what are the different operating modes of 555 timer? So, it operates in 3 different modes. One is monostable mode, bistable mode and astable mode. So, in monostable mode, you will be having one stable state. In bistable mode, you will be having two stable states. In astable mode, you won't be having any of the states, or you can say that any of the states are not stable. So, it is called astable mode. So, now let us understand the astable operation. So, before understanding the complete circuit, first I will explain this. So, in this part or in this block circuit diagram, you can see R1 is the resistor, R2 is a resistor and C is the capacitor that is connected externally to 555 timer. So, this is the 555 timer. To this 555 timer, you are connecting resistor R1, R2 and capacitor C to this circuit. So, how we are configured this circuit, or how we have actually designed it? So, let us see here. So, look at this. Here you can see that there is an in this astable operation, you can see this is the 555 timer IC, right? So, if you can see these dotted lines, this is nothing but the 555 timer IC. To this, you are taking VCC connected with R1, R2 and the capacitor C1 here. So, R1, R2 and C are connected. So, the first point we have to make note here is the capacitor C charges from pin number 8 through, that is the voltage is applied to capacitor through the resistor R1, R2 and then it is flowing to capacitor. Okay. Once the current or the charges will flow to capacitor, the capacitor will start charging. It will start charging. So look at this diagram. From here, from the point 0, the capacitor will start charging now. It will charge to 1 by 3 times of VCC. Once it reaches 1 by 3 times of VCC, I told you that triggering point and, or you can see here, triggering point and the threshold point are connected to the capacitor charging point. So that whatever the capacitor charges are there, that is given to directly to triggering and threshold points. So first the triggering point is activated or triggering point is highlighted with the voltage 1 by 3 times of VCC. Okay. So when this is equal to 1 by 3 times of VCC, obviously the same voltage is also present at this point X. Right? At the point X. So look at this. At point X you have 1 by 3 times of VCC. The same thing happens here. So at the same thing, point X is at 1 by 3 times of VCC. Now comparator 2 will work. It will work and it gives a signal to yes. It will give a signal to yes. Now the input of yes is 1. Input for S is 1. So until then we can assume that the output of comparator 1 is 0 because still you don't have any voltage at this point 6. Therefore it is 0. So because the output is 1, input S is 1 here, the Q bar will be equal to 0. Q bar will be equal to 0. The output is complement of Q bar, so you will be getting 1 here. You will be getting 1 here. That is, you will be having a 1 at the output until the capacitor keep charging. So it will keep charging and reaches 2 by 3 and reaches 2 by 3 times of VCC. Your output will remain 1. Your output will remain 1. Now the capacitor reaches the charge or it will attain the charge 2 by 3 times of VCC. Once it attains the charge 2 by 3 times of VCC, here at point 6 or at the pin number 6, you will be having 2 by 3 times of VCC. Now this 2 by 3 times of VCC is compared with the other one 2 by 3 times of VCC. Okay. So now the output of the comparator 1 will be equal to 1. The output of the comparator 1 will be equal to 1 and here it is not valid because already this comparator has done this job. So here you will be having 0. Here you will be having 0 and the output of Q bar will be now equal to 1. So when it is equal to 1, you can see that the same 1 is given to the base of the transistor. The same 1 is given to the base of the transistor. So now you have the base of the transistor is connected here. Therefore, this transistor will turn on. Transistor will turn on and you can find the capacitor having a direct path to discharge here. The capacitor will have a path to discharge here and the output is complement of this one. So it will be equal to 0. It will be equal to 0. Therefore, the output will fall to 0. So again, once until your capacitor continuously discharged to 1 by 3rd of VCC, you will be having the same 0 state. Once it reaches 1 by 3rd of VCC, again your output will raise to 1. Hence the capacitor will charge. Again the capacitor will start discharging. Your output will go to 0. So this is how the charging and discharging of the capacitor takes place in a stable multivibrator. Understood? So the next one is charging time and discharging time. Before telling that, so make note that this is the charging point. This charging point is due to the resistor R1 and R2. Okay. So, and the next point, this is discharging time. This discharging time is mainly due to R2. It is mainly due to R2. So, the charging time depends on R1 plus R2 into the capacitor C, and discharging time depends on only R2. See here, it is taking only the path R2. It is not moving or it is not going towards R1. Therefore, R2 into C will be the discharging time. So, this will be equal to the discharging time. Now, coming to the derivations of charging time and discharging time, from the waveform shown in the figure above, the capacitor C starts charging from a voltage plus 1 by 3 times of VCC and charge until VCC. But once it reaches 2 by 3 time of VCC, it will start discharging. That is, this is the charging time and this is the discharging time. This charging time starts from 1 by 3 times of VCC to 2 by 3 time of VCC, right? So, VI, input voltage, is 1 by 3 time of VCC, and what is the full voltage? It is equal to VCC. And what is the capacitor charge? Maximum charge what capacitor can hold? VC equal to 2 by 3 times of VCC. Therefore, I can write T1 is equal to R1 plus R2 into C, because both R1 and R2 are responsible for charging of the capacitor. Therefore, R1 plus R2 into C into log of full voltage minus starting voltage, that is on voltage, and full voltage minus the final voltage. So, whose value will be equal to R1 plus R2 into C into ln of 2, that is natural log of 2. So, if you subtract this and if you take the ratio, it will be equal to 2. So, on time will be equal to, what is the value of ln of 2? It is 0.693. So, you will be getting as T1 is equal to 0.693 into R1 plus R2 into C. So, this is the equation used to find the charging time, T on time of capacitor, T on time of the given waveform. Next, discharging time. To find the discharging time, so from the figure, that is from the same circuit diagram, so if you just look at the discharging path, it is from 2 by 3 times of VCC to 1 by 3 times of VCC. Okay. So, here what is the full voltage? It is equal to 0. So, 0 minus 2 by 3 times of VCC minus 1 by 3 times of VCC. Here, which is the resistance responsible? Only R2, not R1. Okay. So, which is equal to R2 into C into ln of 2. So, again you will be getting T of is equal to minus 0.693 R2 into C. This is the discharging time. Or T of time. It means that on time and off time. So, if this is a square pulse or a rectangular pulse, in this rectangular pulse, the time required or time in which your pulse remain in on or maximum value is on time, and the time where the pulse remains in minimum value is called off time. Okay, this is on time, and this is off time. Okay, this is off time. So, on time and off time are defined here. Clear? The next one is some important definitions what you need to understand. So, what is a period? Total period. The time duration where it covers complete phase. So, here it is starting at 0 phase. Again, it reaches the 0 phase. So, what is the time duration? That is your period. Okay. So, it should have the same phase. Okay. So, that is your period. So, here we can define it, because it is a pulse, rectangular pulse, I can define it by on time plus off time. So, what is the on time? It is 0.693 R1 plus R2 into C. What is off time? 0.693 R2 into C. So, what is common here? R2, right? So, if I add R2, your expression will be 0.693 R1 plus 2 times of R2 into C. It is clear? Yes. Next is frequency. What is frequency? Number of cycles per second will give you the frequency. We know that frequency is equal to 1 over T. So using the same formula, you can calculate the value of frequency. So 1 divided by 0.693 is 1.44. So you got this expression, right? Next, what is duty cycle? So this is little important. So might be this is the first time you are listening to duty cycle, or you might have heard what is duty cycle. Okay, so coming to duty cycle, so it is on time by total period. So look at this. So look at these 4 different waveforms. So all these 4 different waveforms have the same period. See, it is starting at this point, ending at this point, starting at this, ending at this, starting at this, ending at this. Starting is here, ending is here. So all the 4 waveforms are starting at the same point and ending at the same point. But what is the difference here? Here you can clearly see that there is a lot of difference in the on time. There is a lot of difference in the on time. See, it is having very less on time. It is having little more on time than this A. Let it be B and C and D. Okay. So C is having little more on time than B, and D is having the maximum on time than A, B and C. So this on time, what is the on time, is defined by duty cycle. What is the on time ratio is defined by duty cycle. So this duty cycle tells us what is the percentage or what is the amount of on time in the given period. What is the amount of on time in the given period of time. So here T on divided by T will explain or will give you the value what is on time. Okay. So T on, we know that it is 0.693 times of R1 plus R2 into C. And what is total period? It is 0.693 times of R1 plus R plus 2 times of R2 into C. So you can cancel C, 0.693693. So you will be remaining with R1 plus R2 divided by R1 plus 2 times of R2. Okay. So this is what duty cycle defines. It defines what is the amount of time where the signal remains on is duty cycle. So if you are expressing the duty cycle in terms of percentage, you will just multiply by 100. We'll just multiply by 100. Okay. So if you just look at that like vaguely, if I want to tell, so I can tell this is having about 30% of on time. Okay. It is not exactly the same. And this is approximately 45% of on time. Okay. And this is more than 50%. Let me take it. It is 60% of on time. And this is having 70%, or it is having 90% of on time. So I can call this percentage as duty cycle here. It is duty cycle. So 30% duty cycle, 45% duty cycle, 60% duty cycle and 90% duty cycle. If you tell that it is 30% duty cycle, it means that 30% of the waveform or 30% of the time period your signal remains in on state. If I tell 60% duty cycle, it means that 60% of the period the signal remains in on state. Okay. So this is what duty cycle refers to. Okay. So that's all for today. Thank you for watching this video. If you have any doubts, you can write me back to my mail ID. And like the video, share with your friends, and don't forget to subscribe the channel. Thank you.